Hey everybody, today's video lesson is going to be on electrolytes. I'm going to talk a little bit about the opposite process that we've been looking at so far. What we've been looking at so far has been the electrochemical cells, and with electrochemical cells what we've seen is that the cell potential has always been positive. Okay, we've always had an increase in voltage, our free energy has always been negative, and our expression, or K, the constant, has always been greater than 1. So all of this means that we favor products when we get to equilibrium. We're going to have more products at that equilibrium point than we do reactants. And that was electrochemical cells, remember, also called galvanic and voltaic cells. Well, this video lesson is going to focus on what's called electrolytic cells, and this is going to be the process of electrolysis. And it's backwards. Here what we were doing with electrochemical cells is we were generating an electric current from a chemical reaction. Here we're going to use an electrical current or electrical energy to make a chemical reaction occur. And that's what an electrolytic cell is. It's a cell that uses some sort of external source to cause a reaction that normally isn't thermodynamically favorable to now happen. Okay, so let's take a look at some ideas here. So the opposite is going to be true for electrolytic cells. So these are non-thermodynamically favorable, meaning that they're not going to produce a reaction. So in order to get that reaction to happen, we have to add energy to do that. All right, so the cell potential is going to be negative, our free energy is positive, and our value for K is going to be less than 1. So notice everything is different, everything's backwards when we deal with electrolytic cells. So it's really important to pay attention to. Right, so the source of electrons in this case is not going to be produced. We're not going to produce electrical current. We're going to use that electric current to cause that chemical reaction to happen. And essentially, we're going to force the electrons to go backwards through the cell. Normally, they should go in one particular direction, but we're going to force them to go backwards in another direction. So our cell voltage is always negative when we deal with electrolytic cells. So when you're dealing with questions on the AP test or just in general, you need to always recognize whether they are talking about an electrolytic cell or an electrochemical cell, because one is going to have negative and the other will have a positive voltage. So when we calculate the voltage, the cell potential is always less than 1, and what this is telling us is that the minimum when we get a negative voltage, it's the minimum voltage that we need to add in order to get that chemical reaction to happen. That's the general idea when we deal with electrolytic cells. So here's an example. We're going to start with taking molten sodium chloride, meaning that we're going to melt it down. So the problem with this is that the temperature has to be really, really high for this to happen, because we're taking table salt and we're turning it into a liquid. So that's why we have sodium ions in the liquid phase and chloride ions in the liquid phase. The idea behind this is that we need to have these ions free to move around. And when they're locked in a solid state, these ions cannot move around, so therefore they can't flow past each other when they're locked in a solid phase, so there's no conduction of electric current. But if we turn it into a liquid and these ions are now free to slide and move past each other, now they can move around. So what we do is we create this molten sodium chloride, melted sodium chloride, and then we stick electrodes in here. Okay, and then we add a battery. All right, so what we have here is we've got at the cathode, the sodium ions are going to go through reduction. So we're always, think about it, if we have a metal ion, whether it's sodium, whether it's iron 2+, we are always going to cause our metal ions to reduce, right? Because reduction is the reduction of that charge. So the metal ions are always going to move towards the cathode. Now what the battery does is that negative terminal on the battery spits the electrons out. So the electrons are going to move out of the battery from the negative side, and they're going to move in to the positive side. So we get the transfer of electrons moving in this direction. Since we get a buildup of negative charge on this plate here, this becomes negatively charged, those positive sodium ions are going to move towards the electrical plate here. Okay, so we get the positive ions attracting here, and as a result, it takes the electron and becomes solid sodium metal. So what you would have is you would have solid sodium metal building up on this plate here as it reacts. Now on this side, you're going to see the bubbles forming. And as the bubbles form is because as the chlorine ion or the chloride ion comes near this electrode, it's going to lose electrons, and it's coming towards us because this is a net positive charge on the anode, and that attracts the anions. Excuse me. And as a result, those chloride ions will then turn into chlorine gas, and then it will bubble out a solution. And again, you can see the reaction that's going on here. So this would be what would happen if we had molten sodium chloride. Now that's a little difficult to work with because such a high temperature. But that is one way that we can get these sodium ions to do something. No, if you think about the past, sodium ions, lithium ions, potassium ions haven't done much. But here's one way that we can get them to form into the solid, actually get them to cause a reaction to happen. Now if we take sodium and chlorine, these two elements back, they're going to quickly, spontaneously convert back in this direction. This reaction is heavily favoring this side of the reaction, not the formation of sodium solid and chlorine gas. If we put these two substances together, they quickly convert back into the sodium chloride. So that's why I want to keep these separate from each other so they don't come in contact again. All right. So I guess that was the end of that lesson. I forgot that I cut it off there, but so that's the intro to electrolytic cells. Obviously, in the next lesson, I'm going to look at electrolysis, and we'll take it from there. So thanks a lot, guys. I'll see you in a little bit.